All right, welcome to our explainer. Today, we're going to dive deep into one of the most fundamental design choices in all of computing. It's a hidden battle, really, happening trillions of times a second inside every single device you own, and it quietly dictates the speed and efficiency of our entire digital world.
You know, it all comes down to a really simple question, but one with some seriously profound consequences. How does your computer's brain, its processor, which is juggling a million things at once, actually know when something else, like your mouse or the network, suddenly needs its attention?
Well, there are two basic strategies, and this analogy pretty much nails it. On one hand, the processor can be like a restless kid on a road trip, constantly asking, is anything happening? How about now? Is there data yet? That approach is called polling. Or it can be like a sleeping passenger who just says, hey, wake me up when we get there. And that is the world of interrupts.
So let's look at polling first. With polling, the central processing unit, the CPU, is basically stuck in a loop. It has to spend its own valuable time and energy actively going out and checking on a device, over and over and over. Got a mouse click for me? No. How about now? Still no. It's pretty simple to set up, but I think you can see how incredibly wasteful it can be.
Now, an interrupt completely flips that script. Here, the CPU doesn't ask, it gets told. When that network card receives a new chunk of data, the device itself sends a signal, literally an interrupt, to the CPU. The CPU then gracefully pauses what it was doing, handles the new request, and then jumps right back to where it left off. It's way more efficient because it lets the CPU do actual, useful work instead of just checking in all the time.
So, what we have here is a classic engineering trade-off. Polling, on one side, is really simple to implement, but it just burns through CPU cycles for nothing. Interrupts, on the other hand, are super efficient, but they require a lot more complex hardware and software to manage all that pausing and resuming. For decades, this was the choice: simple and wasteful, or efficient and complex.
Okay, so let's take this out of the theoretical and into a place where this choice isn't just academic, it's a multi-billion-dollar problem. I'm talking about the modern data center, the very engine that powers the internet.
You see, in the world of high-frequency trading or giant cloud services, a microsecond, that's a millionth of a second, is an eternity. And researchers found that the supposedly efficient interrupt method was adding a huge delay, anywhere from 6 to 10 microseconds, just to get a message from the network card to the right piece of software. They gave it a name: the killer microsecond.
And to put that number into perspective, check this out. Research from Huawei showed that the actual time to physically move data across a superfast data center network can be as little as 1.6 microseconds. So you're spending 5 to 7 times longer just waiting for the system to wake up than you are actually doing the work. That's a massive, unacceptable bottleneck.
So why on earth is it so slow? Well, it's because the traditional path is this long, winding road. The network card sends a signal. The first CPU core to grab it might not even be the one that needs the data, so it has to send another signal to the correct core. Then the main operating system has to wake up and figure out which specific application gets the data. Every single step adds another one of those killer microseconds.
So, when you're faced with a fundamental problem like this, what do? Well, if you're the researchers behind a project called FastWake, you don't just try to tweak the old system. You decide to reinvent the whole process from the ground up.
And what they came up with is just brilliant. They brought polling back, but they did it in this incredibly smart, targeted way. They have a dedicated part of the CPU that does nothing but check the network for new data at lightning speed. By completely bypassing the slow operating system, it can hand the data directly to the right application in just 0.3 microseconds. It's like polling on steroids.
And the results, they're just staggering. FastWake cuts that end-to-end delay from over 10 microseconds all the way down to just 2. That's a performance jump of almost 80%. They didn't just fight the killer microseconds, they completely slayed it.
But hold on, raw speed is only half the battle. That super-fast polling method, well, it works by keeping the CPU pegged at 100%. And that brings us to the other massive challenge in data centers: wasted energy.
This quote from a really important paper by Google just nails the problem. Energy proportional. It just means a server should use power based on how much work it's doing. You know, sip power when it's idle, chug it when it's busy. But they don't. A server that's doing almost nothing still draws a ton of power.
In fact, if you look inside a big data center, most of the servers are just sitting around, running at maybe 5 to 20% of their capacity, waiting for a sudden traffic spike. But here's the crazy part. They're burning power like they're running at 50 or 60%. It is literally like leaving your car's engine revving in the driveway all day. just in case you need to go somewhere.
Now you might be thinking, wait, don't CPUs have sleep modes to save power? And yeah, you're right, they do. They're called C-states. The problem is, waking up from these really deep sleep states can take hundreds of microseconds, way too long for those critical applications we've been talking about. So what do the data center operators do? They just turn them off, and all that power goes to waste.
So, the solution was to invent a better way to sleep. A project called Agile PKC created a new, much lighter sleep state. Think of it more like a power nap. CPUs can jump in and out of this state in under 200 nanoseconds. That's over 250 times faster. The result? They cut the energy use of a typical server application by up to 41%, with pretty much zero impact on performance. Incredible!
And this whole idea, this tension between waiting and interrupting, it goes way beyond just networks and power. It's fundamentally changing how other really complex systems work too, like databases.
Just imagine a database is running some huge, hour-long analytics report. In a traditional system, if a tiny but super urgent task comes in, like processing a new sale, it just has to get in line and wait. But new systems like PreemptDB can now use what are basically software interrupts. They can pause that long-running report, let the urgent task cut in line and finish, and then restart the big job right where it left off.
So, here's the real takeaway. We are moving beyond this simple binary choice of polling or interrupts. The future is all about building hybrid, adaptive systems. Fastwake, for instance, actually has both its super-fast polling mode for critical stuff and an improved power-saving interrupt mode for everything else. It can choose the right tool for the right job in real time.
The future isn't about picking a side in this hidden battle. It's about having an entire arsenal of smart, flexible strategies, both polling and interrupts, and using them intelligently to get the absolute best of both worlds, maximum possible speed with the minimum possible waste. This whole shift from these rigid trade-offs toward dynamic, intelligent systems, it's a huge deal in computer science, and it really leaves us with a final, big question to think about. What other fundamental either-or choices in technology that we've accepted for decades are just sitting there waiting for a similar kind of hybrid revolution?